In this video, we'll break down how memory is managed in Rust using the stack and the heap. This is a common concept across many languages, but we will put a bit of a focus on Rust. Programming languages arrange memory into these two distinct entities so they can be independently optimized for their roles. So understanding how they work allows you to write safer, faster, and more efficient code. But it also provides context into how the ownership model works, which I'll cover in a future video. The stack follows a last in, first out order, meaning you can only add and remove items from the top. It's divided into stack frames, where a new frame is created whenever a function is called. These frames store the return address, so the Rust runtime knows where to resume execution after the function ends, and any local variables. It's important to note that only fixed size variables, like integers and booleans, can be stored on the stack. By organizing the stack into distinct stack frames, the Rust runtime can efficiently manage memory, automatically allocating a frame when a function is called, and deallocating it and any variables declared within it when the function returns. Let's demonstrate a code example where we walk through the stack allocations to help understand it. We start off with a simple main function, which is allocated a stack frame which only contains the return address for the operating system once the program exits. We then call foo, which is assigned its own stack frame, containing the return address to main and its local variables. Finally, we call bar, which again has the return address to foo and some of its own local variables. Once these functions finish executing, their stack and its local variables are immediately deallocated. This pairs perfectly with the ownership model, preventing memory leaks through deterministic memory management that is handled through the Rust runtime. The heap, by contrast, is for dynamic data that can grow or shrink during runtime. Assigning data on the heap is slower than the stack because it requires an allocator to first find free memory. There are a variety of different allocators that are useful depending on different situations. Allocators typically make a trade-off between time, as in how long it takes to find free memory, and the chance of heap fragmentation. Heap fragmentation occurs when a program assigns a lot of small chunks of memory that are allocated and then freed. This breaks up the heap's contiguous block of memory, preventing future allocations. This usually isn't a problem, and if it is, it's worth experimenting with some other custom allocators that have implemented a variety of strategies to mitigate this issue. I'll put some links in the description if you're interested. Pointers are a bit of an exception and are stored both on the stack and on the heap. The process for storing pointers is the allocator will first find an available block of memory for the data and return a pointer to it. The return pointer has a fixed size, so it can be stored on the stack. And as we covered earlier, the stack automatically handles the deallocation of variables inside stack frames. This can be extended to pointers in the underlying heap data. This is managed via the drop trait, which is defined in the standard library and is implemented in the various types of pointers. When the pointer goes out of scope, Rust will call the drop trait implementation for that pointer, which will typically handle freeing the allocated heap data. This is one of Rust's most powerful features, and is one of the main reasons why it doesn't need a garbage collector. I'll be covering this in more detail in a future video. Thanks for watching. Hope this video gave some insight into how memory is managed inside Rust programs, to provide a better understanding of why you need to do things a specific way when writing Rust.